you could escape, but there's no stopping chemistry. So here we go. We're going to go through our lesson this week. Last time, you'll remember that we looked at a calorimeter and we did some calculations with our calorimetry experiment. And what we said at the time was that when those first examples, we were going to ignore the heat that the calorimeter absorbed, right? But the reality is, if you're going to do calculations that are as accurate as possible, you actually need to take the calorimeter into account. So that's what we want to talk about first today. If you go to page 392 in your book, and I'll stick a shot of that in the video, that's our chart of specific heat capacities. And if you remember, the specific heat capacity is the amount of heat it takes to raise a specific mass of a substance 1 degree Celsius. The specific mass of a substance. So specific heat capacity is related to a specific mass. Well, and it's the specific mass of a particular substance. That chart's got just a single substance on there and the specific heat capacities of that substance. However, the calorimeter is actually composed of different types of substances. There's the inside of the walls of the calorimeter. There's the thermometer that's sticking down in there. There's a device that's used to stir the liquid that's in there. And so those things are made up of different substances. So because of the complexity of the calorimeter, we don't really look at the specific heat capacity because it's more than one substance. Instead, we look at just the heat capacity. And the main difference between the heat capacity and the specific heat capacity is really when you're looking at a value, you can tell which one is which, because if it's the heat capacity only, it will not have a unit in there for mass because it's not related to the specific mass like specific heat capacity is. It takes into account the entire object. And so the easy way, all of those values that we were looking at in that chart on page 392, they had units that were joules per grams degrees Celsius, right? But if you're considering just the heat capacity, you're going to be missing this gram unit here. So it'll just be joules per degree Celsius if it's a heat capacity value, okay? So we have a slightly different formula, right? If you'll remember when we were talking about specific heat capacity, we used this formula. We said Q equals C times, C was the specific heat capacity, this is the heat, specific heat capacity, the mass, times the change in temperature. Well, since heat capacity isn't related to the mass, then the formula for heat capacity is going to be simply Q equals capital C, which stands for heat capacity, times the change in temp. So you'll see that mass unit is missing, that mass value is missing there. So make sure you memorize this formula. We're going to need that for some of those problems, and there'll be some of those on the test. So let's go ahead and do an example now on page 401, example 13.3. So if we look at that particular example, it says a 250 gram sample of an unknown metal is heated to 350 degrees Celsius. So we've got a 250 gram sample. It's heated to 350 degrees Celsius. And it's then dropped into the calorimeter, that contains 1,500 grams of water. So 1,500 grams of H2O, that's the liquid that's in your calorimeter, which was initially at a temperature of 24.2 degrees Celsius. So initial temp is 24.2 degrees Celsius. And then the water reaches a maximum temp of 31.2 degrees Celsius. So max temp 31.2 degrees Celsius. If the heat capacity of the calorimeter is, so the heat capacity of the calorimeter, that's our capital C value. If C is equal to 1,400 110 joules per degree Celsius. What is the specific heat capacity of the metal? And so we're trying to find little c, right, of the metal. So let's see if we can figure that out. The first thing that we're going to do is we've got to, if you'll remember last time we said that the value of the relationship between the heat of the liquid and the heat of the object that's in there and the heat of the calorimeter is we know that by this formula here, that the Q of the object is equal to the Q of the liquid plus the Q of the calorimeter, right? Our last examples, we ignored Q of the calorimeter. We said it was negligible and we could ignore it. But now we want to take that into account, okay? So if we're going to try to find out the little c of the object, that's the point of this whole experiment, right? Then we're going to have to calculate these values here of the liquid and then the calorimeter. And from that, we can figure out the Q of the object. And then we can use our formula that we said was, Q equals little c times mass times change in temp to find out what the specific heat capacity is of the object, all right, of the substance that we put in there. Okay, so let's see if we can track that down. First of all, we'll start by finding the heat of the water, right? The heat that takes place in this experiment of the water. So the way that we do that is we're going to use this formula here. We know, I told you to memorize this particular value. We know that the specific heat capacity of water is going to be 4.184 joules per grams degrees Celsius. We know how much water we had to start with, that it was 1,500. I'm sorry, not 1,500, it was 150 grams. And we also can calculate the change in temp. So let's do that first. The change in temp for the water, remember change in temp is the final temperature minus the initial temperature. So for water, the final temperature was 31.2 degrees Celsius minus 24.2 degrees Celsius for a final value of 1.9. Oh, wait a minute, I'm sorry. Am I on the right page? I'm not. Scratch all of that. Scratch all of that, guys. Actually, we're not going to scratch it all. Right? It's just taking long enough recording this, so just scratch this, just that part, okay? I was right. It was 1,500 grams of water. I just was looking at the wrong page. So here we go. Let's figure out the change in temp now. So it is, in fact, 31.2. I was right, actually, on that. I shouldn't have erased that. It was just the calculation that I did there was wrong. So change in T is equal to 31.2, the final temp, degrees Celsius, minus 24.2 degrees Celsius. And I wrote down 1.9, and I'm like, wait a minute, that's not actually right, because that value there is actually 7 degrees, right? So 7 degrees Celsius is our change in temp. So now the Q of the liquid, what's the heat absorbed by the liquid? It's going to be and actually the way that we wrote the formula was mass times little c times that. So we'll do it just like I gave you in class last week. The mass of the water is 1,500 grams. So 1,500 grams, right? Times the value that we memorized, 4.184 joules per grams degrees Celsius, times 7.0 degrees Celsius, which was our change in temp. And so the final value is 44,000 joules. That's the heat for the water, right? But now we've also got to figure out, if we're going to figure out what the total heat is in the system that was absorbed by the system, we also have to figure out how much heat was absorbed by the calorimeter, right? And so how are we going to do that? Well, this is our new formula, right? We said that for the calorimeter, Q is equal to C times change in temp. Well, we we're given C for the calorimeter. We said that was 1,410 joules per degree Celsius, right? And then the change in temp, what's the change in temp for the calorimeter? Well, if you remember, the calorimeter is always the same temperature as the water. So whatever the water started out as and finished as, that's exactly what's happening with the calorimeter. So our change in T is going to be exactly the same. It's going to be 7 degrees Celsius again. So our value for Q for the calorimeter then is going to be 9,900 joules. All right. So we've got Q for, this is Q for the water. This is Q for the calorimeter. Right? And we said that the Q then of the object, we can calculate that using this formula. Q of object equals Q of the liquid plus Q of the calorimeter. And so in our case, it's going to be 44,000 joules plus 9,900 joules. And then we add that together and we get 54,000 joules. So then what is Q of the object? It's the negative of that, right? So Q for our object is 54,000 joules. This is the object, the unknown substance that some unknown metal that we dropped into the calorimeter. This is the heat that was released by that object as it cooled down and heated the water in the calorimeter. Okay, so we're going to have to make some room here, because remember, what are we trying to find? We're trying to find the specific heat capacity of the object, right? So we're just going to make us some room at the top here, because now that we found the heat that was released by the object, then this is going to be simple, right? So it's just simply a matter of taking this equation here. If Q equals M times C times change in T, and we're trying to find out what little c is, then we just have to rearrange the equation and say that little c is equal to Q divided by M times change in T, right? And so Q in this case is 54,000 joules. The mass of our object, we were told, is 250 grams. So 250 grams. And then the change in temp for the object, we actually haven't calculated that yet. So we need to know what the change in T for the object is. Change in T of the object. What we do know is that the final temperature, everything's the final temperature, is the same temperature at the end, right? So at the end, everything is 31.2 degrees Celsius. But then we take that final temperature and we subtract what the initial temperature was, and the object initially was 350 degrees Celsius. So our change in temp for the object was negative 318.8 degrees Celsius. All right? Does that make sense? I can't hear you. Oh, I love it. I can't hear the students. I love it. Not really. I rejoice to hear your lovely voices. So, all right, so let's figure this out. So this was our equation. So we're going to plug in this negative 300 and, I'm sorry, I left off the negative here. Negative 318.8 degrees Celsius there. And so our final value, the specific heat capacity for this unknown metal, is 0.68. We got to make sure we get our units right. Joules per grams degrees Celsius, right? So that is our final answer. So it was a long problem. It took us a little while to get to that, right? But nothing was particularly hard. We really only needed two equations, right? We had to use this equation here for both the heat of the that's released by the object, as well as the heat that's absorbed by the water. And then also we had to use our new equation that we just learned, which was for the calorimeter, the heat that it absorbs is the same formula but without the mass in it, right? So just those two equations there. As long as we can figure out the change in temperature, we're good. I'll see you on the next video.